Hello, my name is Kevin Davis. I'm here to give the second talk in my series on my hypothesis. During the last talk, we just introduced the question of negative dimensions, and this time I want to delve further into this by asking the old age question, how long is a piece of string? Now we can see this piece of string is about 50 centimetres long, 18 inches. We can measure it, and I call this the real length of the piece of string. And at the first level of understanding, we say that the perceived length of the piece of string is exactly the same as the measured piece of string L, the real length. In the second level of understanding, I'm going to introduce another term, which is the term we used for the handkerchief illustration, the unreal term minus L. And therefore we can say the perceived length is now a function of the real and unreal lengths. We can calculate what the perceived length is by adopting a diagram such as this. This was introduced by Michio Kaku in his book on hyperspace. And we can put the real length along one axis of this graph and the unreal length on the other. By putting in the figures plus L and minus L, we can calculate, by using the Pythagoras theorem, the perceived length L. You can see that it gives us a result that the perceived length L is plus or minus the square root of 2 times the real length L. I don't know what the significance of the square root of 2 is, but I do notice that we have now a plus or minus option in the answer. Going on further to the third level of understanding, we introduce a third dimension. There's the real, the unreal, and IL, where I is the imaginary dimension, and equates to I is the mathematical function, the square root of minus 1. It's a symbol for the square root of minus 1. Doing exactly the same treatment, this time with the extra dimensions, we now have to do a three-dimensional graph with real along one axis, unreal on the other, and IL, the imaginary term, along the third axis. But again, using exactly the same technique, we can calculate now that the perceived length of the piece of string L, again given by Pythagoras theorem, gives us the amazing answer plus or minus L. In other words, with these two extra dimensions, we would still perceive the length of the piece of string that we have right at the very start. I think this is a staggering conclusion. Indicates why science is not getting to all the answers of all the paradoxes in nature. There is a minus the unreal value as well, which we will come to a little bit later on in my talks. So far we have only been thinking about the one-dimensional piece of string. Does it apply also to volumes? Well, if we have a look at this little box here, we can see that it has got length, depth, width. If we call those A, B and C, we can then say that the volume of the box is A times B times C. But with the new understanding that we've talked about previously, the perceived volume is now plus or minus A times plus or minus B times plus or minus C, which simply comes down to plus or minus ABC, which equals plus or minus the measured volume. So it applies also for volumes. But it's interesting to note that there's nothing in these equations that tell you what form this could be. It could be a sphere, it could be a manifold, it could be anything. And I choose to think that it also can be thought about in terms of space-time. So in other words, the perceived space-time, using the same extra dimensions, the real, the unreal and the imaginary dimensions, just equates to plus or minus S. In other words, the space-time that we can perceive and measure by telescopes and what have you is exactly the same, although now there are two extra dimensions. Can we go further? Well, I believe we can. But what is the next dimension? The third extra dimension apart from the real? Well, if we have a look at the coefficients of these terms here, we'll notice there's +1, -1, pi. These are 3 of the fourth roots of 1. So for our next dimension, we will just merely use the -I coefficient. Introducing this into the equation, we're going through exactly the same calculations. I can't do the drawing because I didn't know how, beyond third dimensional drawings, how to draw it. But I can assure you that the equation still holds and that the perceived space-time now is plus s, the small 1 squared, plus minus s squared, plus is squared, plus minus is squared. And this gives us a big fat 0, a nothing. But bear in mind what I talked about earlier when I was talking about nothing and exact nothing. We can see that the real terms, the plus s and the minus s squared, are exactly cancelled by the imaginary terms. This is exactly what I defined nothingness right at in the very first lecture. So this is a perfect 0. Space-time in these extra dimensions, 3 extra dimensions, gives us a perfect 0. No residues, no remainders. There is absolutely nothing there. And that concludes the second talk today.